Dear students and participants of the course on railway engineering, today we are going to discuss about the circular curves which are provided on the railway tracks. If you remember, in the previous lecture we started discussing about the speeds. The speed is one of the important element in the geometrics which influences the various design features. While discussing the speed, we did talk about the dynamic effects of the speed, and then we talked about the various definitions related to the speed, and finally there were computational efforts with respect to the calculation of the safe speed on the track, the permissible speed and the equilibrium speed. And then towards the end we have talked about the speed restrictions. Now talking about the today's lecture is focused on circular curve. So this circular curve means we are coming from a straight section and then there is a requirement of a change in the direction. Therefore, this curve has to be provided. Now when we talk about this curve, there are different elements of the curve which needs to be looked at. So there we will be talking about the radius which needs to be provided. We will also be talking about the versine which should be there between the actual curve which is being traced and the chord of the curve. So this is the length and this one is the chord. So between this at the center point, whatever is the maximum distance which is coming is versine. And then we will be talking about the measurement in the field, that how these curves are being laid. There are different methods of doing it. So looking at those particular methods, we will see that what are the requirements and how it can be done. So let us start with our discussion. Now curve is what? It is an arc which joins two tangents either in the horizontal direction or in the vertical direction. That means we may be talking about the plane of the profile, or we may be talking about the elevation of the profile. Now when we say that we are talking about the plan of the profile, as I said, it may be looking like this form. So there are two straight sections of the track. So this is also straight, and then a curve is being provided in between so as to connect those two straight sections. So this is in the plan. The other condition can be that we are moving on a track and this profile has certain gradients. Say it may happen there is a gradient of 1 in N1 and then it is being followed by another gradient of 1 in N2. Now at this location where these two gradients are meeting, a kink has got formed and this kink should not be there in the track. So what we do is we just smoothen out and we are going to provide a curve in this form. So that is in the case of elevation. So in both of these cases these curves needs to be there, and how these can be provided, how these can be laid in the field, that is what is the focus of today's discussion. Now these are required to make a change in the direction of the movement of the train. So it can be in the plan, it can be in the elevation also, in any of the directions it can happen. So if you are talking about in a plan, then it is being termed as a horizontal curve. And if you are talking about the connectivity of the two gradients, as I said here, one in N1 with one in N2, then at the point of their contact, at the point where these two gradients are intersecting with each other, at that particular point whatever the smooth curve is provided, so that is defined as a vertical curve. So we are going to discuss these things. But there are certain objections in the provision of the curve, that why we should provide these curves, curve should not be there. Now some of the objections which are there, they are related with either the smooth riding or the use of the rolling stock, or the possibilities of certain type of eventualities which may happen. Like the first one, it says it prevents the use of heavy locomotives. Say if you are talking about a curve where you are going with a straight section like this, and then there is a sharp curve, and again this is a straight section. Now, in this sharp curve, it will be difficult for the heavy locomotives to move at the speed at which it is required to move on a particular track. So, there may be a requirement of restricting the speeds. In some of the cases, this sharp curve may be such that the locomotive may not be able to traverse that particular curve. So, this is one such sort of a restriction, and that is where the objection arises that the curves or the alignments or the profiles which are provided, they should be such that they can be universally usable. Another thing, as I said, the eventualities can be there. When you are talking about the curve, what is happening? At any of the curve, some force is going to be exerted in the outward direction, which we talk as a centrifugal force. And this centrifugal force is equals to mv square divided by r, where m is the mass, v is the speed, and r is the radius of the curve. So, this is the radius of the curve here. Now, depending on the way this is being provided, there is a possibility of overturning or there is a possibility of derailment. Now, the curve which is being provided here, this is provided for a speed equals to v. But the trains which are moving on this curve, they may be moving with a speed v1 which is greater than v, or they may be moving with a speed v2 which is less than v. So, there are two situations which are getting induced here. So, in one case, if we have provided this curve and so as to counteract the centrifugal force, what we do is we provide a super elevation like this. So, can also be termed as cant. Now, in this particular case, for a speed v, if this cant is being provided and now the speeds are more than that, it means this is not going to be sufficient. There will be more of the centrifugal force which is going to be affected in terms of the square of the speed. So, there is a possibility of the overturning, or there may be a case when the speeds are lower. So, it means the cant which is being provided is more than what is required, and there is a possibility the vehicle will move towards the inner side and a derailment may happen. So, this is another objection with respect to the curves. Unequal distribution of the load on the inner and outer rail at the axle wheel location, wherever the wheels are touching the rail. Now, in one case, if we talk about the rail section, so it will be something like this. So, there is a cant of 1 in 20 which is being provided at the bottom. This is a normal thing which is already there, and the separate cant which we are talking is with respect to the centrifugal force. Now, the elevation differences are going to be there. So, with the interaction of the wheel, what is the force which is coming on inner or outer rail, that is important. So, if this is inner rail and this is outer rail, if this is not being balanced, this P1 and P2, if this P2 is higher, then more wear will be there. There is a possibility of a lateral thrust, there is a possibility of opening of the gauge. So, all these problems can happen. That is where when we design it with respect to a cant, we try to see that P1 becomes equals to P2. There is a equal distribution of the loads on both of the rails. Running is not smooth on curvature. Of course, there is a curvature resistance, and because of that resistance, the issues will be there. There will be a reduction in the speed also. We have discussed about these when we talked about the track resistances. And many fittings are required against the forces which are acting on the circular curve. So, you have the thrust which is coming towards the outer side. Lateral forces are there. There is a possibility of overturning of the rail. There are moments and twisting moments which are going to be induced at that particular location. So as to counter those, the fittings are required. So, the number of fittings may increase at this particular location. So, it is increasing the cost, it is increasing the requirement of maintenances, and that is the point from where the objection arises, that if we are providing the curves, these are the problems which we face. Now, let us talk about the locations where the curves shall not be provided. If they are required, they should be used before or after those locations. So, what are those prohibited locations? The very first one, bridges or tunnels or viaducts. So, we have a river and we are providing a track which is going across this particular river. Now, if a curve is provided here, say if it is something like this, then it is going to be a problem. So, it is always better that we have a straight section at this point, and then the curves are provided if at all required after or before those locations, and the same is the case in the tunnels also. From operational point of view, from the construction point of view, both you can look at, and that will define that if it is a straight section, then that is the most economical section which you will get. The bridges approaches very nearer to the bridge. It should not happen that the bridge is provided and the curve is coming like this. No, this is not a good design. It is better that if you have a bridge, then even if curve is there, at some distance before the bridge and at some distance after the bridge, it should remain straight, and then only the curve should be there. So, this is required because in that case the loco pilot will be able to see the stretch, the section, and will be able to take a appropriate decision if there is a requirement to take that. Level crossings. Level crossings means you have a rail section which is passing like this. So, maybe there is a double track being provided and there is a road which crosses this section. So, this is a rail section and this one is a road section. So, in this case, when this type of a crossing is there, it is better that the crossing is at right angle, and we have discussed about it when we were talking about the alignment. So, they should be at right angle, and if there is a requirement of a curve, they can be provided here in the case of road also, as well as in the case of track also, they can be later. Deep cuttings. In the case of deep cutting, the cutting is already a very costly affair. It is going to increase the cost of the total construction. So, it is better that in the case of deep cuttings, as small section as possible should be there, and that is possible when you are talking about a straight section rather than a curved section. In the case of steep gradients, when you have talking about the steep gradient, so one resistance is already coming and that is very high, which we have discussed that it is W into G, if you remember. And at the same time, if the curve is also provided, then these two are going to provide a combined effect, and that combined effect will further induce problems in terms of the speed as well as in terms of the weight which can be hauled. So, there is a issue here. So, in those particular cases, we should not provide a curve because this will add on otherwise to WG. In the station yards, most of the things should be more or less simpler. So, they are having more straight stretches. So, that is one area where we should try to prohibit unless until there is no other option. The yard approaches, the yards where the sidings are being provided, where the trains which are going to be received are going to be dispatched before they start their journey from a station. So, on those approaches also it is better that we have a straight approach being provided rather than a curvilinear approach being provided there. Now, let us look at the various elements of a curve. The very first thing, the curve is defined by a degree of curve which is notified as d. So, here you can see there is a curve being shown and this is a pivot point. Say let us talk about this pivot point as O and the curve is from A to B. The radius of the curve is being defined as r. Now, when we are talking about this curve and the degree of curve, what we do is we take a chord length and this chord length is taken as 30.5 meters or 100 feet. That means you have this a distance from here to here as say 100 feet or 30.5 meters. Now, this 30.5 meter arc or 100 feet arc, when you join them in this form, then whatever is the angle which gets created here is the degree which we are talking now. So, considering this the geometry or the properties of this particular section, what we can have is that this d degree with respect to the 360 degrees. So, d divided by 360 is there with respect to the another ratio which we can take here is the length of the arc with respect to the perimeter. So, length of the arc is 30.5 meter, r is the radius, so perimeter is 2 pi r. So, that is from the property of making this, and that gives us the formula that d is nothing but 1750 divided by r. So, if the radius is being given to you, we can calculate the degree of the curve, and vice versa. If the degree of the curve is being given to us, then we can calculate the radius. Now, one thing which we need to see is that the smallest radius and the largest degree, how they are going to be controlled? They are going to be controlled by two features. One is related with the vehicle and another is related with the geometry. So, in the case of the vehicle, it is wheel base. What is the distance between the bogies and what is the length of the vehicle? So, that needs to be taken into consideration. And another is the sharpness of the curve. So, sharpness of the curve can be defined by the value r, how big or small this value is. On the basis of that, certain values have been given for a broad gauge track. So, if it is a plain track, then in that case it is 10 degrees is the maximum degree of curvature which can be taken, and this 10 degrees will translate into 175 because the relationship is 1750 divided by r, or if I put as r is equals to 1750 divided by d. So, if it is 10 degrees, that means 175 meters is the value. If it is 8 degrees and this 8 degrees is provided on a turnout, there the value of curvature is going to be 218 meters. Now, one other thing which we discussed was the versine. We said in the very starting we will be discussing about it. Let us look what is this versine and how we can calculate it. We can go back to the diagram which is shown on the right hand side. This is the center of the overall curve or this circle. So, we have a chord which is Mn. So, Mn is the chord of the curve, and if we talk about MLN, then this can be considered as arc. So, the length of the curve is going along this arc and the chord length is different. Just at the center, that means the point P, whatever is the distance between the point on the curve and the point on the chord is versine, that is V. So, this V is nothing but here it is LP is equals to V. So, that is written here also. Now, let us go back and look at the geometry here. In that geometry, if we are taking this LP and PQ, then the multiplication of these two is going to be equal to MP and PN. So, this is from the curve geometry. So, from the geometry what we are writing is LP into PQ is equals to MP into PN. Now, LP is what? This is V and this is nothing but this is LQ minus PQ. Okay. So, here we are talking about the values, or LP is when you look at here LP is V. So, we have talked about V, and PQ, okay, we calculate now PQ from this, that will be equals to LQ minus V, and LQ is nothing, this is LO plus OQ, and LO and OQ they are radius. So, this is OQ is radius and this is also OL. So, that means this is 2R and this 2R minus V is the value. So, considering 2R minus V here and V, and when we talk about MP and PN, the P is the point which is the bisector point of the whole chord. So, it means the length of the chord is C. So, it will be C by 2 into C by 2. So, considering this, what we get is V into 2R minus V is equal to C by 2 into C by 2, or C square by 4. Now, when we take this value of 2R into V, or V square, now because of this radius, this value is becoming a very big as compared to V square. So, that means this V square can be neglected, and if we neglect this V square, what we get is 2RV is equals to C square divided by 4. And if we are interested to find out versine, then the formula becomes C square divided by 8R. So, if all the units are same, then we can calculate from this particular formula. But if we are interested to get the value of V in centimeters, then the formula will change a bit, it will become 12.5 C square by R. You can make the changes, you will get this value, and if we are talking in terms of mm, then it is nothing but 125 C square by R. Here C and R, they have been taken in meters. So, depending on how, in what particular value you want to get it, you can use one of the formula. Now, measurement of degree of curve, let us correlate this measurement of degree of curve with the versine. Now, what we do is that we have already discussed about curved section in this form, and this is the chord which we discussed, which was Mn, and this was versine. Now, so as to find out the degree of the curve, what we do is we take a chord of 11.8 meters. So, if we take a chord of 11.8 meters, it means it will be somewhere here like this. So, this chord can be 11.8 meters. Now, if we have taken this 11.8 meters as chord, and this becomes equals to C, and we have an equation that V is equals to 12.5 C square divided by R in centimeters. And if we put those values here, we put R is equals to 1720 by D, or the another formula which we can take if we are considering it in terms of the dynamic gauge. So, then that can be 1750 divided by D. So, if we take those values, then what we get is, we get V is equals to 1.011 D. So, it is more or less equal. So, V is equals to D. So, it has been observed that if you take a chord of 11.8 meter and go on the track and put this chord there, so your track is moving in this direction. Now, you put your 11.8 meter chord here, and you just calculated the center of this 11.8 meter chord, that what is this value. So, whatever you get here, that can be transformed into the degree. So, this is the property which is used for measuring the degree of the curve in the field. Now, how we are doing this is that another thing which we can consider here, measurement of a versine here. The 20 meter overlapping chords are used where the versine measuring stations at 10 meter intervals. That means, whatever is the total length is being taken at every 10 meter intervals. So, this is 10 meters, this is 10 meters, this is 10 meters. We are going to take the measurements. And while doing this, what we do is we have a wire or a nylon cord or a fishing cord which is stretched between the end of the chord length. So, if this is the end of the chord length, so this one is M and this one is N. I am again correlating it with the previous diagram which we have discussed. So, we just stretch between them. Then the distance is measured between this cord or wire and the gauge face. So, the track is going here. So, whatever is this gauge face is, So, gauge face will be on the other side, so inner side. Okay. So, if the one rail is being provided at this point, so this is the gauge face, and this is being measured at the center of the chord. So, at this center, whatever is this value which we are getting, then R is equals to 125 c square divided by V, where versine is in mm. So, you have got a versine in mm, chord is being known to you. On the basis of that, the radius now can also be calculated. So, vice versa, you can calculate V and put it in R, or you can do the other way, that you can calculate V and get the value of D, that is the degree of the curve. Now, there are some other elements which we can talk now in the case of circular curve. So, one diagram is being shown here. This is the point of pivot point where the rotation is taking place. So, see it is O, and say this is point A, and that is the start of the curve. This is point B, which is the end of the curve. Now, what you can see here is it is written as TC and CT. What is the meaning of this TC and CT? This is a one standardized notation which is used. Now, here this section is a tangent section, which is a straight section. Similarly, here also this is a tangent section, whereas this one is a curved section. So, TC says that you are moving from tangent to curve, whereas CT says now you are moving from curve to tangent. So, that is the way these 2 points are being marked. Now, AB is the length here, if you are talking in terms of a chord. So, it is being considered as C. Length of the curve will be along the track profile. So, it is this particular length being defined. So, you can see that this is the length here. There is a difference between the chord and the length, which is at this level being shown as m. This is nothing but it is basically a versine. Then if we extend the tangent in this form, and then the another side direction also we are talking. So, these two are meeting at this point. So, this is the point of intersection or interchange. At this point, whatever angle gets created, this is the change of direction. So, this angle we are considering here. Now, if we just join this point of intersection with the point O, about which the all curvature is being taken up, then it divides the whole section into 2 symmetrical parts, which are having the value of delta by 2 and delta by 2. Considering all of these things, now let us look at the elements. The length of the curve L. So, length of the curve L we are talking, which is A, B, this one. Now, when we talk about the angle, angle is what? Angle is the arc divided by the radius. So, this angle is arc divided by radius. Arc here is AB divided by R. So, when we talk about AB arc, is that is nothing but radius into delta, and that is what we have written here. So, this is in radians. You can convert it into degrees. You can use the property again, how it can be converted. So, depending on this angle, you take say 360 degrees, or you are talking about 180 degrees, you can change it. Tangent length T. Now, tangent length T here, if say this is a point P, then the tangent length here is nothing but this is AP. Now, let us talk about the triangle AOP. So, we have this triangle AOP. In this triangle, because this is a tangent, so this is going to be 90 degrees. And this is angle is delta by 2 here. So, considering this, you know the radius, now you have to calculate the tangent line. So, we are taking the property of trigonometry. So, tan theta is nothing but this is the vertical arm at right angle versus the base. So, looking at that, so it means tan of angle. So, whatever angle is there, it is nothing but it will be AP divided by OA. So, AP is nothing but AP means OA will come on this side, and that is where OA here is R. So, it is R into tan of angle, and angle here is delta by 2. Then versine is here we are talking as m. Now, this m will be how much? If you talk from O to the point here, say this is Q, then OQ is R. Okay. So, if we are talking m, now this m we are considering is here, say if this is L is already there. So, we can say take it as F this point. So, we are interested with the m is F q and this is O q minus O f. O q is already known, this is R. Now, for O f we can use triangle O A F. Now, when we are using this triangle O A F, then this becomes 90 degree. Now, when this becomes 90 degree, then what will happen? So, again you are using the property of a right angle triangle. What we can find out is this R cos delta by 2 is O f. So, this O f is R cos delta by 2. So, R minus R cos delta by 2 is the value. That means, you need not to remember all these values, you understand the geometry, and on the basis of geometry you can always get the formula and use it. Similarly, if we talk about offset E, so this is an offset E. Now, this offset E, if we are considering again a triangle OAP, then this OP can be calculated, because you know the tangent length here, or you know this radius R here as well as angle. So, this OP can be calculated, and from OP if you remove OQ which is R, then you will get it. So, R divided by cos of delta by 2 minus R is the value which will be there. Similarly, if you have to find out the length of the chord C, which is AB. Now, this AB is nothing but it is 2 times of AF, and again for AF we can go to a triangle AOF. So, we know R, we know the angle, so we can find out AF. So, AF is, we are finding it here, and on the basis of that finally we make it double. So, we make double. So, 2 into R of sine delta by 2 is the value which we will get. Now, let us look at a numerical here. The bearing of the first tangent and point TC is north 70 degree east. So, we are talking the bearing here. Now, you must already be knowing about this bearing system. So, this is north. So, this angle we are talking, because in this case this is east. So, the angle is given as north 70 east, whereas the bearing of the second tangent at the point CT. So, this is point CT. Again, if this is angle, the north direction is there, and we are getting this particular angle which is given as north 70 west. So, if we consider this, then in that case we can get this value and this value based on this angle as well as this angle. So, this angle is 70 here and this angle is also 70 here. So, considering this angle of 70, now this becomes 20. Similarly, in the other case this becomes 20 if we are going to work with the quadrants. So, when we work with the quadrants, the delta comes out to be 40 degrees. Now, the rest of the things are simple. We have discussed already about the various elements and how we can calculate those elements, considering that we know the radius and we know the angle delta. So, length of the curve is L, that is R into delta, and then we are changing it into degrees. So, it is pi divided by 180. So, the length which we are getting here is 139.63 meters. Similarly, tangent length is R 10 delta by 2. Now, R is known to you, so you can find out this value here. Sorry, the R is given as 200 meters. So, here this is written wrongly. So, this should have been 200 meters. Kindly make a change here. Now, similarly, if we talk about versine, so for versine also we have to look at, I think in all of these calculations the things have changed. So, I will request all of you to make those changes, because the R which is being given is 200, but by mistake the length is being considered here instead of R in all of these cases, same here as well as here and here. So, the values may change in this particular case. We will provide you the solution separately for this particular numerical. Now, let us look at the setting in the field. So, setting in the field, like there are different methods which can be there. One is the tangential offset method, long chord offset method, chord deflection method, theodolite method, and quartering of the versine method. Let us look these one by one. Now, tangential offset method, it is used for the setting of the short length curves, which are of up to a length of 100 meters. And these are also used for laying the turnout curves. What is the procedure in this? The procedure is that we extend the tangent line. So, this is the tangent line which we have discussed, and the curve is being provided in between. So, this tangent line is being extended. Measure a chord C1 from the tangent point. So, this is the TC point. From here we can measure the chord C, say this is C here, that it comes up to this point. Measure the offset O, which is C1 square divided by 2R at right angles. So, from here at 90 degree we are considering the offset, and this offset is given by the length of the chord square of that divided by 2R. Now, this becomes the first point on the curve. Now, we can repeat the process. We can take another chord of the length and then again the distance from here, and then we can get another point at 90 degree considering the offset. So, this is what is being shown here. You have the curve, this is the tangent point. From this tangent point, the first distance is being taken as C1, the offset O1 is being calculated, and then we got the point A. Then again we have moved on the tangent, we have come to point B, which is equal to chord length C2, and there the offset O2 is being calculated, and then we go 90 degree to that tangent, we will get a point B, and similarly C or similarly D. But now in this case there is a problem, there is an obstruction here. That means if I extend this tangent further, I will not be able to pass through this obstruction. So, it is better that as soon as we have got a points like this, we can create another tangent here. And now, let us take the distances from on this particular tangent as C1 dash, C2 dash and so on, and then from there O1 dash, O2 dash, O3 dash. These are the points which we are going to get once we calculate this. So, it means if there is an issue in the field, this is one of the way you can solve it. The another method is a long chord offset method. Now, in the long chord offset method, what we do, this is also being used for the short length curves. Here both tangent points should be visible. So, this is one tangent point, this is another tangent point. They should be visible, it means there is no obstruction between them, and then we can have this chord, and this chord is being divided into equal parts. Say there can be 8 equal parts. Now, as soon as we have 8 equal parts, now this is the center point of the chord. Now, we have already found out that how we can calculate the versine. So, the versine can be calculated here. Now, once you calculate the versine and you get 90 degree, what you will get is a point S. So, point S is available to you. At this point S, a parallel line is being made with respect to the chord. So, these two lines are parallel. Say if this line is PW, so PW is basically parallel to T1, T2. So, this is one geometry which we have got. Now, what we are going to do is from this one which is tangential to the curve, we are going to get the offsets at distances. Similarly, on this direction. And once we get those offsets, which we have calculated using a formula previously as the length of the this chord is square of that divided by 2r. So, this value will be available to us O1, O2, O3. We also know the value of V. That means, if you are going with respect to the chord T1, T2, and if we take a distance which is equals to V minus offset I, then what we will get is these distances as Vi. So, we will get V1, V2, V3, and that will give us the points A, B, C or D, E, F, whatever number of points are there, and that is how this curve can be generated. So, the same thing is being defined here. The long chord distance between the tangent is divided into equal parts, and so say it is C by n, where n is the number of parts. As I said, usually we go for 8 parts. The concept of versine is being done. So, versine is C square divided by 8r. We calculate that, and C is the distance between the tangent points T1 and T2 which are visible to us, and on that we have already created a line like this. Now, considering the offsets are calculated for different distances from the center point of the long chord, and then the offset is x square divided by 2r, where the x is the value of that distance which we are considering from here. So, that is the value we will get. So, finally, the offset from the long chords, because this one is the long chords, from here offset when we are talking is this one, that is V1, V2, V3. So, this is versine minus x square divided by 2r, and that is the same thing which I have told you before. The third one is the chord deflection method. So, in the case of chord deflection method, we are going to use the deflection of the chord which is being taken with respect to the initial point and then subsequent points. This is one of the popular methods on Indian Railways, and here this is also suited where there is a problem with respect to the number of obstructions which may be there at different locations. So, it is a confined area, restricted area, so it becomes easier to work with this one. So, what we do here, the length along the curve is divided into equal parts of the chord length, say x, and the last chord in that case, it is not necessarily that everything is 100 meters, you divide by 10 you will get everything as 10 meters, sometimes say it is 108. So, last one will be 8 meters. So, there is a change in the last chord which can be say x1. Now, offset for a chord x is calculated, which is x square divided by 2r. So, you have gone to x distance and you have calculated the offset here, which is x square divided by 2r. Now, first of all what we do is from the point of intersection we go back and mark the point T, which is the tangent point. Now, once we have done this, then we move along the tangent line for a distance x, which is the distance in which the chord has been equally divided, and from there we will have a chord, and that chord will be moved here for a distance of say offset x square by 2r. So, we will get a point here. So, what it says is starting from the tangent point, a tape of chord length x is taken along the tangent length, and then from there it is swing inside for a distance equals to offset, which is x square by 2r. So, we are getting the first point. Now, what we do? Now, we join the tangent point with the first point and extend it, and on this extension again we take the distance x from this point. Now, this becomes our tangent, and then again we will swing it from here. So, we will get another point. So, now join the tangent point with the first point in the curve, extend on the curved one, take a distance x on it and swing the tape towards the inner side, and so as to get the another point, and then again it will keep repeating in this form and we will get the different points on the curve. In the case of the last point, because there was a difference in terms of the length, the offset is going to be calculated as x into x1 into x plus x1 divided by 2r. And using this formula, once we get that final value of offset, we will do that and we will get the last point on the curve. The next method is the theodolite method. In the case of theodolite method, again this is also a method which is widely used on Indian Railways. It uses a theodolite, it uses a tape. It is also known as a Rankine's method. In the case of surveying, you must have studied about these methods. Now, what we are doing here, we have a tangent point at this location. We put our theodolite at the location T1, and then the line of sight is being made towards the point of intersection Pi. So, this is the setting of the theodolite which is being done. Now, what we need to know is the deflection angle by which we are going towards the inner side. So, there are two values which we are talking here. One is defined as delta capital and another is a small del. So, the angle subtended by a 30.5 meter long chord we have already talked about, that was talked as d is equals to 1750 divided by r. Now, this tangential angle for 30-meter chord is delta by 2. Now, it will be half of it, and now if we convert for a x meter, so it is delta by 2 divided by 30.5 into x. So, we will get this degrees. So, what we get is now the delta is equals to 1721 into x divided by r. This is how the value of a small delta can be calculated. Now, when we start with the first reflection angle, then in that case the capital delta will be equals to the small delta. But when we go subsequently, this small delta is going to be used, it is going to be added to the previous capital delta like this. So, we are getting the deflection by this particular angle actually. So, what we are doing? We have a theodolite here, it is being put in the line of sight towards the point of intersection, we swing it by angle delta. So, what you will get is this line. Now, on this line, then we have already talked about the length x here. So, considering that length, what we will do is we will swing the rope here on this side, and wherever it cuts the line of sight of the theodolite, we will get the first point. So, set the theodolite at the start of the curve, rotate by an angle delta to move the tape with 0 at the tangent point for a distance x. So, the first point is noted. Now, for the second point, from here again you are going to move by delta. So, you will get another line of sight, and then from here you will move the tape with a distance x on, and you will get a point here, and the same method is going to be repeated again and again. The last one is the quarantine of the versine method. What we do here, it is again one of the simpler methods which we can be used. Now, we have this tangent points T1 and T2, but these should be again visible, and we can mark the distance between the them. So, we have marked it like this. Now, at this center point, we can calculate the versine V. So, versine V is c square divided by 8r, where c is nothing, but it is T1, T2, and that is known to us. Radius of the curve is also known to us. We can calculate the value of V, and at 90 degree we can measure this distance, and we will get a point A here. Now, what we do? We just join the tangent point with point A here, or similarly on the other side. Now, our next chord is C1 on this and C1 on here. If we put this C1, we will get another value of the versine, and at the center of this chord we will get a point B. Now, next we will again join the first tangent and the point B. Now, this becomes C2, and for C2 we will get a versine, so we will get a point F. So, this is a procedure which is repeated again and again. So, we keep going this procedure, and finally, this is how we are going to get all of the points on the curve. So, with this we close our discussion on the circular curve now. What we have discussed about the various relationships between the radius of the curve, the degree of the curve, the versine, and then we talked about the various methods which can be used so as to lay the curve in the field. So, there were around 5 methods which we have talked, and some are being used on the Indian Railways. Thank you. We will be meeting in the next lecture. Bye.